So now that we laid the groundwork for rotational motion, we can derive a couple equations, which should be familiar from linear kinematics. And these are for constant acceleration. And so this IFF is if and only if. So if and only if the angular acceleration is constant. So these equations only apply if we have constant acceleration. If it's not constant, then you have to use some calculus. But we'll derive our first equation. So working from the definition for acceleration, which is the change in angular velocity over time, we then can break it out, and letting the initial time be 0, we get to here. And then just doing some little algebraic manipulation, multiply t over and then move over, we come up with our first kinematic. The angular velocity is going to be the initial plus the acceleration times time. And this is exactly like the one for linear motion, which says that the velocity is the initial velocity plus the acceleration times time. And that's what we'll see with all of these. So all of our linear kinematics have angular counterparts. The second one, so we start with the definition of angular velocity. And angular velocity is the change in angular position with respect to time. And again, doing the same thing that we did over here, we get to this point. So our average angular velocity, and we can do the average because it's constant acceleration, would be our change in position over time. But since it's an average, then it's also equal to the final plus the initial divided by 2. That would give me my average angular velocity. So now we can set these two quantities equal to each other because these are both equal to the angular velocity. So we get this. And then again, so doing one algebraic step, we just multiply t to the other side and we end up with this expression. And then what we're going to do is we're going to substitute right here. Because this we already derived. That's this equation, and we've just substituted in. Now multiplying out, I'll leave the algebra for you, but multiplying it out, you get this, and then you move it around, and there's your, you screwed it down just a little bit. Oops, way too much. So there's our second one, our angular position. And again, this has, this is the same as our linear, 1/2 AT squared. And then finally we get our other one, that's absent of time. I'm not going to go through the derivation. I did that for the linear, but there it is. So we'll have this one as well. So we have those three kinematic equations. So let's do an example and apply it. A DVD is spinning at 27.5 radians per second when it begins to slow down at a rate of -10 radians per second squared. What is the angular velocity at 0.3 seconds, and how far has it rotated in this time? So before you start tackling these, make sure that you understand what's happening. So draw a quick picture. We have a disk rotating, or close to a disk. And since the angular velocity is positive, that's rotating in this direction. So my angular velocity is this way. And then the acceleration is negative, so my angular acceleration is this way. So this thing is slowing down. All right, so we want to know what's the velocity. So part A, angular velocity is going to be the initial velocity plus the acceleration times time. So this is just a substitution problem. The initial velocity is 27.5 plus the acceleration, -10 times the time, 0.03. One of these seconds will cancel one of these, so we get the same unit, so we can add all that stuff up. And we get 24.5. radians per second. B, how far did it go? So how far did it go? Well, that would be my position. So the initial position plus the angular velocity, the initial, times t, plus 1/2 angular acceleration times t squared. And again, it's just a substitution problem. We'll put the initial at 0. The initial velocity was 27.5 times 0.3 plus 1/2 of the acceleration, -10, times 0.3 squared. And you get 7.8 radians. And that's it. We might have to convert that into revolutions. So you could do like 2 pi radians is 1 revolution. So you could do something like that. You could get it into degrees times 1 revolution over 360 degrees or whatever. But that's it.